Hi, I'm Prof and welcome to Chemistry Matters. And today we are going to be talking about states of matter and how we depict these, how we explain these, and all sorts of other good stuff. So let's kick off by talking about what it is we mean by states of matter, and let's consider the good old water molecule. For example, we think of water as being a liquid because that's the way that normally it appears to us under our normal circumstances, certainly here in New Zealand anyway. But obviously if you go to colder climes, then water exists as ice. If you go to much hotter climes, or if you boil your water or whatever, you'll find it will turn into a gas. And so those are the three what we call states of matter. The solid, the liquid, and the gas. There are others. We're not going to get into those more exotic beasties today, okay? So, solids, liquids, and gases. Why are some things solids? Why are some things liquids? Why are some things gases? What are the properties that define each of those phases, as we call them, of matter? And how do we move between them? How do we go from a solid to a liquid to a gas? So first up, let's consider solids. Now what are the defining characteristics of solids? Well, if you had to think of one thing about solids is, well, hey, they're solid, okay? And being solid, it means that they basically don't really move, that you can't really sort of compress them or anything like that. The molecules, the atoms, whatever that make up solids are rigidly bonded to one another, and it takes a lot to sort of move those things. So if we were going to put it in a couple of words, solids don't flow, okay? They're rigid things. Liquids. Liquids definitely flow. That's one of the properties of a liquid, but they don't fill up any container into which you put them, okay? So you pour a liquid into a container, it only fills the bottom part of the container, okay? So liquids flow, but they don't completely fill a container into which you place them. Gases, on the other hand, you put a gas into a container, it fills the whole container. So gases flow, and gases will fill the whole of a container into which you put them. Okay, so why the difference? What are the sort of defining molecular or atomic, I guess, characteristics of these three phases of matter? Why are solids solids? Why are liquids liquids? Why are gases gases? It's all to do with intermolecular, so between molecules, or in some cases interatomic forces, okay? Now, the intermolecular or interatomic forces in solids are strong, okay? So the atom positions or the molecular positions in solids are pretty stable. There's not a lot of movement in the molecules or atoms of a solid. That's why they don't flow, okay? So in other words, we're talking strong intermolecular forces there. Liquids, you've got weaker intermolecular forces, although they're still, relatively sizable. And gases, the intermolecular forces between those are very, very small indeed. And that's why they go and completely fill a container into which you put them. So what type of forces are these that we're talking about? Well, there are three main types of forces that are involved in matter. Well, there's obviously lots of different forces, but in terms of these forces determining solid, liquids, and gases, we're going to only consider three. So the first of these is a force called dispersion forces, okay? So now for some reason, and I don't know why, dispersion forces have got a whole lot of different names. So you might know these as van der Waals forces. You might know these as instantaneous dipole forces, okay? So how do these work? Well, this is kind of interesting. Now, these forces usually are pretty weak. They are thought of as being the weakest intermolecular forces that you can get. So let's take a non-polar molecule that looks like this, okay? And the blue is showing the electron density in this isolated non-polar molecule. And the electrons are evenly distributed between the two nuclei there. There's a nucleus, and in the blue is your distribution of electrons. It's even. Okay, So let's imagine that a molecule of this now comes up to a molecule of that as well, okay? So two of these molecules are now going to come up and come close to each other. Now, what have we got? We have got a positively charged nucleus here, okay? Which obviously is attracting the electron density in this molecule, but it can also instantaneously attract some electron density in a neighboring molecule. And when it does that, it's going to pull that electron density towards it a little bit, and it's going to mean that instead of this electron density being now totally symmetrical, what it's going to do is going to make it a little bit asymmetric. It's going to distort the electron density in that molecule. And in this diagram here, that shows you what's happening, okay? Here is your nucleus that has got the little positive charge. It's going to pull electron density from that neighboring molecule towards it. Now the red areas depict excess negative charge, the blue-purple areas depict excess positive charge. So in other words, one end of this molecule is going to become a little bit positive, delta positive, and it then is going to attract the electron cloud from a neighboring molecule. It's going to make that a little bit negative, and what you've got then is a dipole. A little bit positive, a little bit negative, and that now is an intermolecular interaction. You're going to get a small intermolecular interaction involving the attraction between slight positive charge and slight negative charge, okay? These are called dispersion forces, or much more sensibly named, I think, instantaneous dipole, because this is an instantaneous process. As soon as those molecules get away from each other, the dipole that was there now disappears, okay? So this is thought of as being a relatively weak force, but for example, this is the force that holds iodine molecules together. Those of you who know iodine will know that iodine is a solid, and so therefore you can get quite strong forces there, okay? The second type of force is a dipole-induced dipole interaction, okay? And so an example of a dipole-induced dipole interaction would be, let's take a water molecule here, and let's take an oxygen molecule here, okay? So our water molecule has got a permanent dipole. So this is a little bit negative. These guys are a little bit positive. The oxygen molecule, again, has got a symmetrical electron distribution around it. Now, so an oxygen molecule is going to come up to a water molecule like this. The water molecule is a little bit negative. Okay, this end of the water molecule is a little bit negative. It's going to attract now the positively charged nucleus of one of these oxygen atoms. And therefore, you're now going to get kind of an induced dipole in your oxygen molecule. And that induced dipole is going to make the electron density a little bit asymmetric again. So we're going to have delta positive and delta negative ends of the oxygen molecule. Okay? So we can see why this is called a dipole-induced dipole interaction. Here is a molecule that has a permanent dipole, water. Here is a molecule that doesn't normally have a dipole, oxygen. And the fact that this is coming up close to this oxygen molecule now means that you're inducing a dipole in your oxygen molecule. And again, as soon as this oxygen molecule diffuses away from the water molecule, that dipole is going to disappear. And this is why oxygen is soluble in water. Remember, oxygen is a non-polar molecule. Water is a very polar molecule. You'd expect oxygen shouldn't be soluble in water. It is to a very small extent thanks to these sorts of interactions. So that's the second type of intermolecular interaction that we're going to talk about. The third type is good old dipole-dipole type interaction, and this is always best explained using the water molecule, which has a permanent dipole, as we've already seen, and so therefore we have an interaction where the negative end of the water molecule attracts a positive end of a neighboring water molecule, delta negative, delta positive, and this is called a hydrogen bond. Okay, where a hydrogen is interacting with a lone pair on an oxygen or a nitrogen or a halide type ion. Okay, and this is a very strong interaction. Okay, this will be the strongest of the interactions that we've talked about. Okay, so those are the forces that hold solids together, liquids together, and gases together. Of course, obviously they don't hold gases together very well, because in gases those intermolecular interactions are going to be pretty darn weak. Okay, so we talked about the defining characteristics of solids. They don't flow. Gases, they do flow, and they fill up the container into which you put them. Let's have a look at a couple of important characteristics of liquids. Okay, and the first of those is a thing called surface tension. Okay, so this is essentially peculiar to liquids, and let's have a look at why surface tension happens. Now, you'll be familiar with surface tension when you see little bugs floating around on the surface of water. You would imagine that they should go straight through. They don't. They can skate on water because of this property of water called surface tension. And this arises from the fact that water molecules that are in the bulk of a sample of water are different to water molecules that are at the surface of a sample of water. In bulk water, every water molecule is surrounded by other water molecules, so you've got equal interactions in each direction. But at the surface, if you look carefully here, you look at these water molecules at the surface. Yes, they've got water molecules below them and beside them, so they're involved in intermolecular interactions there. But above them, what have they got? They've just essentially got, well, air molecules, if there is such a thing, molecules of nitrogen, molecules of oxygen, and those interactions are going to be extraordinarily weak. It's pretty much like they're not there at all. And this then creates surface tension. The fact now that these water molecules at the surface are busy pulling on neighbouring water molecules quite strongly and trying to get them into a sphere. And this is why if you let water do its own thing and form droplets, they are spherical droplets. So this is the basis of surface tension of water, a property peculiar to a liquid. And then we also have another property of liquids, very important, and this is called vapor pressure. Okay? And so when we look at a liquid, it might not be obvious, but above that liquid there are going to be gaseous molecules that have escaped from the liquid and now sit above the liquid. And that's true of all liquids, okay? So let's consider just a hypothetical liquid situation here. And we are going to we're going to put a liquid into an evacuated container. And so in the gas phase, we have nothing. So what's going to happen are molecules from the liquid are going to escape. They're going to evaporate into the gas phase, and now they start floating around in the gas phase. As soon as they do that, they can go back into the liquid phase. And then you're getting more and more and more gas phase molecules formed from the liquid phase. You're getting more and more and more gas phase molecules going back into the liquid phase. And eventually you get to a situation called equilibrium, where the rate at which molecules leave the liquid phase is the same at which molecules enter the liquid phase, okay? So you've got them going out and you've got them coming in like that. And the whole concept of vapor pressure is extraordinarily important, as we will see in the next video, where we're going to talk about the interconversion between phases of matter, between solids and liquids and gases, and how we display that on things called phase diagrams. Okay, so we will see you in the next video.